name is Chris Harris and I'm from Alawi Chemistry, and in this video we're going to be looking at equilibria and rate of reaction. Now this video is mainly looking at the bridging of material from GCSE, which you will have learned, going into A-level. So it has little elements of GCSE content and it has some from A-level. So some of this will seem fairly familiar to you. And some of it will be quite new. So the whole point is to really give you a little bit of a head start if you are going to study A-level chemistry in the next year or in the next couple of months. So, like I say, they're designed for that particular purpose. And chemistry is a really tough subject at A-level. It's a very rewarding one, but it's a very tough one. So, what I've done is I've created a whole range of different A-level chemistry videos tailored to the main exam boards such as OCR, AQA, Edexcel and OCR Salters, and they are under my Alawi Chemistry YouTube channel, so go and have a look on there and subscribe and see if they can help you all the way through A-level. Also have created a set of questions regarding this video. The questions are electronic, so you can click on it. They're all multi-choice. So you can click on it and get your answers straight away, because it actually marks itself as well. So if you click on the link in the comments box below, and you'll be able to see them there. So let's make a start. So this one, we're going to start looking at reversible reactions. You will have seen reversible reactions at GCSE, and then I'm going to introduce some new concepts here for A-level. A-levels, a lot of A-level is to do with utilising key scientific words and really integrating them words within your language, because examiners are looking for them types of terms. So you'll see there's a lot of key phrases that I'm going to use here, and I'll emphasise them as well as we go through. So a reversible reaction is something that goes forwards and backwards. So it has a reaction that goes both ways. In reversible reactions, we have what we call a reversible arrow. So this arrow here that you see on the screen is symbolises a reversible reaction. There are many reactions which are reversible as well. So here's a generic example. So A plus B will produce C plus D, but also C plus D will also produce A plus B. So it's a reversible reaction. So what we see with a reversible reaction is two sides to it. So let's look at the forward one first. So initially, in the forward reaction, you can see that reactants are used up quickly, but then slow as their concentration drops. So you can see here on this graph, as time goes, the amount of reactants decrease because they're being used up. The backwards reaction, initially, the reactants are reformed slowly because there isn't many products there in the initial phases, and obviously as the reaction proceeds, you get more and more products. So if you've got more products, then as the reaction goes on, then you've got a higher chance of collision, and therefore you've got a higher chance of reforming your reactants again. So we see this typical curve, but it's starting the other way. So initially we have no products whatsoever, as you can see there. So we have no products, but this then rises over time. So we reach a point called equilibria, and at this point the forwards reaction equals the rate of the backwards reaction. So it's all to do with the rate of reaction, how quick a reaction is going. We call this a dynamic equilibrium because the rate of the forward reaction equals the rate of the reverse reaction, and the concentration of the substances remains constant. That's key. So we're not saying that the amount of reactant and product is the same at equilibrium. That's really, really important. That's quite a key point where particularly people at A-level, they get a bit confused about them points about what equilibrium means. So it's about the rate. And equilibrium is established at that point there where it's marked on the graph. Now, this only occurs in closed systems. So a closed system is basically a system where substances can't leave and no other substance from outside can get in to interact with it. So in other words, it's a bit like having a beaker. Your reaction's going on in that beaker there, and we put a lid on top of that beaker, and effectively that blocks any external factors having an influence on that. So that's what we call a closed system. Clearly, if there wasn't a lid on, you might get some substances evaporating, so that means your product has been lost to the surroundings, which does have an impact on the reversible reaction. Okay, so you may or may not have come across this fella before in a GCSE, but he was a Frenchman, and he was effectively famous for coming up with a principle that explains how reactions behave in different conditions. So this guy was called Le Chatelier, and he basically stated what would happen if we change conditions to an equilibrium reaction. So there he is there, so handsome chap. So Le Chatelier's principle, he said if a reaction at equilibrium is subject to a change in pressure, temperature or concentration, the position of the equilibrium will move to counteract that change. Okay, his principle is better understood if we look at loads and loads of examples, and that's exactly what we're going to do here. But this is where you really have to use your key terminology here to explain what's going on. Okay, so let's have a look at this example. So if the change in condition results in equilibrium shifting to the left, we make more reactants. So in this case, if we do something to the pressure, temperature, or the concentration, and we'll look at these examples later on as well, we'll go through this in detail, but if that results in it shifting to the left, then we have more reactants being produced. So in this case, we're producing more hydrogen and nitrogen and less ammonia, which is NH3. Likewise, if we go the other way, so if we change the reaction conditions and that, as a consequence of that, that shifts equilibrium to the right, then we get more products. In this case, we're producing more ammonia. Okay, so I've put Le Chatelier's principle up there right at the top, just as a reminder, but we're going to look at one of the factors that can influence the position of equilibrium and what that can do, and this is concentration. So if we increase the concentration of a reactant or a product, the equilibrium will shift to try and reduce the concentration. So the opposite will happen if the concentration is decreased. So in other words, if we increase the concentration of the system, the full system, then equilibrium will shift to try and reduce it. So it's always doing the opposite. It's constantly trying to adapt or shift to counteract the change that we've made to it. So this only works in homogeneous equilibria. Don't worry too much about this. This just means that the reactants and products are in the same states. In other words, they're all liquids, or they're all gases, or they're all solids. All these reactions here are all going to be homogeneous, by the way. Okay, so if we increase the concentration, we bring back this, and you might have seen this reaction at GCSE, which is the Haber process. It's the way in which we make ammonia. So if we increase the concentration of hydrogen, equilibrium will shift to the right to use it up and reduce the concentration, and more ammonia will be produced. So if we increase this here, so we've got this system, we then put more hydrogen in there, equilibrium will shift to try and use that up or get rid of the excess that's been added. So that means it will shift to the right to produce more ammonia. Okay? And likewise, if we increase the concentration of ammonia on the right hand side, then it will shift to the left to use it up and reduce the concentration, so we get more hydrogen and nitrogen. So if we have this reaction and then we decide we're going to put more ammonia into that externally, let's say, then what's going to happen is equilibrium is going to shift to the left, and so we don't want more ammonia, so it will basically break down to form hydrogen and nitrogen again. So this is the effect on concentration. Okay, so let's look at another influencer, which is changing pressure. So if we increase the pressure in equilibrium, or if we increase the pressure in the system, the equilibrium will shift to try and reduce the pressure. So this is exactly the same as concentration. It's going to shift to try and reduce the concentration of what you've just increased. This is related to pressure. So this is more akin to gases. So again, this only works in homogeneous systems. So if we increase the pressure, if we increase the pressure, then the equilibrium will shift to the side with the fewest number of gas particles. And this will reduce the pressure, and in this case, we're going to produce more ammonia. So if we increase the pressure in this system, now we can see here, the equilibrium is going to move to the side with the fewest number of gas molecules. So you can see here, the number of gas molecules we've got on the left is 4. So we've got 3 hydrogens and 1 nitrogen. On the right, we've only got 2. So equilibrium is going to move to that side to try and free up some space, because we've increased the pressure. Effectively, we've decreased the size of the container. That's one way in which we can increase pressure, is by decreasing the size. So this is going to shift towards the side with the fewest gas moles, which is going to be NH3. So we're going to get more ammonia. So if you're in the industry of making this, that's one consideration you can take, because you think, well, actually, I want loads of ammonia. So if I increase the pressure, I'm going to get a good yield of ammonia. So this is where it actually comes into it, especially in commercial environments. And likewise, if we go the other way, so if we decrease the pressure at equilibrium, in other words, that's like making the container bigger, so we're giving the reaction more space to react in, then the reaction will shift to the side with the most number of gas particles to increase the pressure again. So it's constantly doing the opposite. You can see it's a bit of a pain. We're producing more nitrogen and hydrogen as a consequence because equilibrium is shifting to the left, but we're not producing as much ammonia. So if you want to produce ammonia, decreasing the pressure isn't a good idea because you're not going to be producing as much ammonia as you could be. Okay, so next one is changing the temperature. So this is another factor which can affect equilibrium as well. So if we increase the temperature, the equilibrium will shift to try and reduce the temperature, and the opposite will happen if the temperature is decreased. So this is where we've got to look at what we call the enthalpy change of the reaction. So in this example, if we increase the temperature, equilibrium will shift in the endothermic direction, and this will reduce the temperature. Now, you might have come across exothermic and endothermic at GCSE, so you know that exothermic means to release energy, so to release heat energy, and endothermic means the energy is being taken in by the reaction. And enthalpy is given the symbol delta H, which is on there. And so what we're looking for here is the forward reaction, and what you'll find on these reactions is you'll see delta H equals and then a number next to it. That is always referring to the forward reaction unless it otherwise states. So in this case, this reaction here moving forward is minus 46.2, so it's an exothermic reaction. So this means that moving forward it's exothermic. So if we increase the temperature in this system, it will shift to decrease it, so it'll move in the endothermic direction. So in this case here, if we increase the temperature, it will actually produce more reactants, not products. That seems a little bit strange because normally you'd think if you heat something up, you're more likely to get more products. But in this example here, because the forward reaction is exothermic, we're actually going to get more reactants. So if you're in the industry for making ammonia, increasing the temperature isn't a good idea in this example because you're not going to get much ammonia. And likewise, if we decrease the temperature, equilibrium will shift in the exothermic direction, which is the forward direction, because this figure tells us that. More ammonia will be produced. So if you're in the industry for making this, it's a good idea to have a lower temperature and not a higher one, otherwise you're not going to get as much ammonia. Okay, catalysts. So catalysts play an integral role in chemistry because remember, catalyst speeds up the rate of a reaction. But catalysts have no effect on the position of equilibrium whatsoever. All they do is they speed up the rate at which equilibrium is established, but they do that by speeding up both the forward and reverse reaction equally. So there's no difference. So adding a catalyst will not make any difference to how much ammonia you produce in that example. So it has no effect on yield, like I say, so it doesn't have any impact on that whatsoever. Okay, so let's look at a particular example. So making ethanol is a classic example. You may not have seen this at GCSE, so this is some exam boards at A-level have this as a requirement that you must know this, but for this purpose it's just to basically apply everything that we've seen there, combining them all together and coming up with ideal reaction conditions. So here's the reaction here. So we've got ethene reacting, there's ethene there, reacting with water to form ethanol. So ethanol is used in hand sanitizers. It's used in the drinks industry as well. So it's quite a wide ranging chemical, and it's a very useful chemical. And tons of this stuff is made every day. So we have an enthalpy here for this reaction is minus 46. Now remember, that is the enthalpy for the forward reaction. So this tells us it's an exothermic reaction moving forward. Okay. So the ideal conditions to make this, and this is through research and through analysing the conditions and seeing what maximises the amount of ethanol we get. But scientists have discovered that the pressure should be 60 atmospheres of pressure, a temperature of 300 degrees Celsius, and a catalyst is phosphoric acid. So the catalyst helps to speed up the rate at which equilibrium is established. So the temperature. So the forward reaction is exothermic, as we've said. So decreasing the temperature will mean that equilibrium shifts to the right and producing more ethanol. So actually, having a lower temperature is a good idea because that increases the amount of alcohol that's produced. Temperature. Key thing though, if we have a temperature, because you might think, well, why don't we just have it at 0 degrees? The problem is temperature. If it's a higher temperature, it means the particles have got more energy and they've got a higher. They're more likely to collide with each other. So a lower temperature actually means we have a lower speed, and that's no good. You might get a really good yield, but it might take you days to make it. So there's a compromise between this. So the compromise is 300 degrees. So that's a compromise between yield, how much ethanol we can make, and how quickly you can produce that. So it's no good having a really low temperature, get a really good yield, but it takes you ages to make it. So that's the compromise there. Pressure. So high pressure means equilibrium shifts to the right, producing more ethanol. So that's good. So increasing the pressure is really good. Less moles of gas on the right. So you can see we've only got 1 mole of gas on the right there, as you can see there. But we've got 2 on the left, so you can see on there. So this is a good thing because if we increase the pressure, then that means we get more product being produced. However, you might think, well, why don't we just have ridiculously high pressures? Well, pressure has its own problems, and that is that it's really expensive because if you increase the pressure of all your vessels making ethanol on an industrial scale, you need really thick walled tubes and pipes and containers to hold this in. That's really expensive to manufacture these really thick pipes, and also it's the cost as well at which we build the manufacturing facility to do it at high pressure, but also the safety. If you have high pressure gases running through your system, you've got a really high chance of something going wrong, and if it does go wrong, it's going to be catastrophic because you're holding gases under pressure. So there's a compromise, and the compromise is obviously 60 atmospheres in this case. Okay, so let's look at rate and collision theory. So this is to do with we looked at little bits here already about collisions and how particles react and what we need to get them to react and altering the conditions. So we're going to look at collision theory. You will have seen collision theory at GCSE. It's very common at GCSE. So this is just a reminder. But for a reaction to occur, they must collide. That's as simple as that. And rate of reaction is basically how quick something happens. So it's the change in concentration or the amount of reactant or product per unit time. So it's how much product is being produced or how much reactant is being used up per fixed amount of time. So, for example, rate is the amount of reactant used or product made divided by time. That's really important. You would have seen that at GCSE when you've done rates of reaction. So particles move all the time. They're not static. They're moving constantly. But most collisions actually don't lead to a reaction. So particles will bump into each other, but nothing actually happens to them. They just move off and do their own thing. So there's a criteria that must be met for it to actually work. So for a reaction to occur, they must collide in the right direction. That may seem a bit strange, but what they've got to do is they've got to collide in the right orientation. So it's a bit like having a bar magnet and having 2 norths together. It's the wrong way around, and they'll just repel and just bounce off each other. But if you have a north and a south, then they will attract. So it's a bit like particles. They must hit in the right orientation. And also, the very important thing is they must have enough energy. If you've got particles that don't have enough energy and they're just sluggishly floating around, they don't have enough energy to actually react. So they'll bump into each other, but they'll not actually react. So how can they be measured in experiments? And you might have done this again. You might have done it with marble chips and acids, for example. You might have done it with sodium thiosulfate, where you get a change in colour. And we'll look at these experiments as well. But practically, we've got to know how we can measure it. So we're going to look at how long it takes for a precipitate to form. You might have done this as well. This is sodium thiosulfate, and it works by putting a cross on a bit of paper, and you slide that paper underneath a conical flask with your reaction in there. And basically what we're doing is we're timing how long it takes for that cross to disappear. Now obviously we've got to look down the top of the flask and see underneath, and if we can't see the cross appearing through the solution, then that's when we stop the stop clock. The problem is this is really difficult to know exactly when that cross disappears. It's quite subjective and it leads to errors. A way in which we can do that is use the same observer. If we're using, say we're using person A to do the observation for the first reaction and person B does it, their perception of when that cross has disappeared is different and you don't get consistent results. So like with anything, it's about trying to reduce your errors and keeping everything the same. The amount of mass loss. You may have seen this one as well, but this is ideal for reactions that produce a gas. Basically, if we have a balance and then we have a conical flask, a gas is produced, that escapes, and that's a product. So we're just measuring the rate at which that gas escapes, and that'll have an impact on the mass of it. It's a fairly accurate method. It's a pretty good method to use. However, if the gas is toxic, it's not a good idea doing it in the open air because it's going to cause some harm. So we have to use a fume cupboard, which is not ideal because there are other ways in which you can do it. Another one is volume of gas produced. You might have seen this one as well. So this is another way of measuring it is using a gas syringe. Basically, it's a similar method to the other one about amount of mass loss, except what we're doing is we're collecting the gas that's being produced and measuring how much is produced at regular intervals. So we do that using a gas syringe, as you can see there, and we do it over a fixed period of time. And basically we monitor how much gas is produced, say every minute, every 30 seconds, depending on how frequently you're measuring it, and we plot that on a graph, which you'll see later. Okay, so rate can be found from the gradient. So we do all them experiments and we plot our results on a graph, and then we can calculate the rate from them results. And again, you would have done this at GCSE. So, for example, in this one, this is a straight line graph. Not all of them are straight line, they can be curved, but we'll look at that later. So this is the volume of gas produced over time, and we've measured how much gas is produced at regular intervals in this case. So the gradient, remember you would have done this in maths as well, so there's a little bit of maths. You'll find there's quite a bit of maths at A-level chemistry as well, but gradient is the change in y over the change in x. So pretty standard equation there. The bigger the section of the graph that you use, the better. So this is a practical skill. When you're plotting graphs, try and use as much of the graph paper as you can. The bigger the graph, the better, the more accurate your results are going to be, rather than squashing it into a tiny graph. So what we're doing is we're trying to find points on y and x which can be worked out easily, and this is quite vital. So here we've got a point here. So we've drawn 2 points. There we are. Okay, so the first one measures 6, so that is the change in x, and then this one is 4, so that's your change in y. So then what we're going to do is we're going to put down them changes there. So the gradient is 4.6 minus 0.6 because that's where we measured it, and then 7 minus 1, which is 6. And so therefore the gradient is 0.67, and you work out the units in a really easy way. The units is always whatever it is on the y-axis over whatever it is on the x-axis. So in this case it's centimeters cubed per minute, and that's the rate. So in other words, if this was volume of gas and that was meters cubed, that would be meters cubed, and let's say if that was seconds, that would be meters cubed per second. Okay, so let's look at a different graph. So this is a curved graph instead, and again you would have done this at GCSE, particularly in maths, where when you want to find the gradient of a curved graph, we have to draw a tangent. So it's a best fit effectively, because it's really difficult to measure it if you don't draw that tangent. So here's one here. So this is the mass of a reaction vessel over time. You can see it's producing a curved line, and we draw a tangent, which is a diagonal line that measures a curve at a specific point on that curve. So we can't do it for all of them. We're going to do it for one particular point. And we extend the line right across the graph, and that allows us to work out the gradient, just for the same reasons we mentioned previously. And the gradient is the rate at that specific point on the curve. So that's quite an important point. So what we're going to do is we're going to work out what the rate of reaction was at 3 minutes in this example here. So what we do is you draw a gradient at 3 minutes, and it must hit, or it must align right at the 3rd minute, which is there. Okay, so that's minute 3, and that's your tangent. We extend that right across. So the gradient is the change in y over change in x. It's exactly the same as what we said before, and so there is our gradient that's just been drawn there. So I'll just go back. There it is. Okay. So there's your changes, 0.8 and 4. We then put that into the equation and we get a gradient of 0.2 grams per minute. So we know it's grams per minute because this is grams on the y-axis and minutes on the x. Okay, so let's look at activation energy. So activation energy is the minimum amount of energy required for a reaction to occur. It's called the activation energy. So this is where we're looking at the enthalpy side, so the energy side required. You would have seen this at GCSE as well, like I say. So an energy profile diagram can show the energy changes in a reaction. So here you can see we've got an energy profile diagram here. We've got enthalpy along the y-axis, and we've got reaction progress on the x-axis. We have reactants and we have products, and we've got our profile that's been drawn in there. So reactants, so molecules, molecule bonds are stretching here as they have more kinetic energy. So we can see basically molecules, if you imagine molecules, you've got your atoms, you've got your bonds between them. So what they're doing is they're stretching and contracting, they're moving around. That's the energy they have. Now if we use that energy and if we heat that up and provide more energy, then that vibration is going to happen a lot more frequently. And if it happens to such an extent, because it's fluctuated so rapidly, it can break the bond as well. So we have something called an activation energy. And again, you would have seen this at GCSE, but an activation energy is basically the difference between the reactants and the top of the profile. So that's the activation energy. So it's basically how much energy is required to get to a stage where we have enough energy to have a reaction occur. So right at the top, like I say, at this point, the bonds have sufficient energy to break, and that's what we want, because for a reaction to happen, we need to start and break bonds in the reactants. So reactions that have low activation energy, so basically that curve is not as pronounced, they have less energy required to break the bonds. And so that means that to get that reaction to occur, it doesn't need a lot of energy to do that. So what affects the rate of reaction then? So this is looking at particle theory as well, or looking at that side and looking at how we can actually get a reaction to go. So particles move around more at higher temperatures. So remember we had our reactants at the start and then products at the end. So to get them to break bonds, we need to put energy in. So this is looking at that part of the curve, but we're looking at it at a molecular level. And so what happens is when particles move around a lot more at higher temperatures, they collide more often. And so therefore, the reactions happen faster at higher temperatures because we've got a much better chance of these particles hitting each other at the right orientation and also hitting each other with enough energy for them to actually react. So the combination of more collisions and more kinetic and more energetic collisions, because they do have kinetic energy, means that the small increases in temperature, just small increases, leads to large increase in rate. And that, once we've got it over that hump that we've seen before, then we start and get products being produced quite rapidly. Okay, so concentration and pressure also affects rate. So we've looked at temperature that affects rate, but concentration and pressure also does as well. So pressure, so increase in pressure will increase the rate of reaction. So the particles are actually closer together, and you can see on the diagram here that we've got a smaller box for higher pressure and a larger box for lower pressure, but you can see the particles are in a much confined space there, and they're more likely to bump into each other, and therefore they've got a higher chance of a reaction. So it's a little bit like putting 10 people blindfolded into a room, giving them a large hall, for example, and getting them to walk around for 2 minutes and seeing if they bump into each other. If you put them into a small cupboard, they're more likely to bump into each other. So it's exactly the same with particles as well. So these particles have, at a higher pressure, they're more likely to bump into each other because there's not enough space for them to move around. It's as simple as that. Another thing as well is concentration. So concentration is much more akin to solutions or liquids, for example, but increasing the concentration will increase the rate of reaction. So particles are closer together, they collide more often, and so therefore there are more frequent collisions and a higher chance of a reaction. So you can see here the box size is exactly the same, there's no difference there, but you see the number of particles, the number of red particles is increased. We've got more of them in that solution, so we've got a higher concentration. And because there's more red particles, there's a higher chance of a red and a blue coming together, and that means there's a higher chance of reaction. So, for example, using, if you've done marble chip experiment, using a more concentrated acid will produce gas much quicker than using a weaker acid. And you might have done that in your experiments as well, where you've changed the concentration of your acid, and that's had an impact on rate of reaction, and this is the reason why. Okay, catalysts also affect rate. Obviously, this is the whole point of using catalysts is to speed up something. If we can manufacture something much quicker, that means it's a lot cheaper to manufacture, and we can get a lot more out per hour or per minute. So a catalyst is a substance that increases the rate of reaction, but what it does is it provides an alternative pathway that has a lower activation energy. So remember from that diagram that we'd seen just before where we had that hump shape on there, if we had a catalyst, it effectively pulls that down, so less energy is required to actually get that reaction to go. But remember, catalyst is chemically unchanged. It doesn't actually change anything. So catalysts are generally used to speed up specific reactions. We have a variety of different catalysts. They all have a different purpose, and you will come across that more often in A-level. You'll see the different types of catalysts that are used, and obviously you'll come across them in reactions as well. But they're used to make a product faster, and they can be used to lower the temperature required for a reaction, and this saves energy and money, and that's a good thing. So, for example, one of the catalysts, we call it a zeolite catalyst. This one's actually it's a solid, but it's covered in micropores. So there's loads of tiny little holes within this type of catalyst that increases the surface area, and that makes it great as a catalyst because it means substances can bond to it and release from it, and you'll see a lot more of that in A-level. But if it's got a larger area for that to happen, it means it can turn over reactions much quicker. So zeolite is an example of that. So how do they affect rate? So going back to that energy diagram that we'd seen before, we're going to bring it back again. So there it is there. Okay, so you can see, remember that bit was the activation energy with no catalyst. If we add a catalyst, it brings that down, and so the activation energy actually drops in this case. So you can see that the catalyst lowers the activation energy, so we've got more particles now have enough energy for them to react. So why do we use catalysts? So catalysts are good for the following reasons. So one of them is to lower the temperature. So that means less money is spent on energy. And so that means we produce less carbon dioxide, because normally when we generate energy, it's particularly if we're using fossil fuels, and we produce carbon dioxide. So if we can come up with a way where we're using less fuel, that's got to be better for the environment. They speed up the reaction as well, which is good because they say in industry time is money. So it's about trying to produce products as quickly as you possibly can. And that's a good thing economically. And also, we can change the properties of a product as well. So, for example, we've got some catalysts. This is just a bit of extra knowledge, really, but such as a Ziegler-Natta catalyst. And what that can do is turn polyethylene to a more dense, rigid plastic at a higher melting point. So we can turn something which is quite soft and flexible into something that's a lot more rigid, and that can be really useful because we're just repurposing one product. So we're not having to make separate products using different raw materials. So that's a good thing. There are environmental benefits as well of using a catalyst. So lower temperatures and pressure means that lower CO2 is emitted, again because we're not using high amounts of energy or fuel to reach them types of conditions. And also less waste is produced as well. As what catalysts can do is it allows scientists to use reactions with better economy, so better atom economy. So you would have seen that, you'll see that in video 6 when we look at atom economy. But instead of producing a product using multiple steps, like 5 steps, we only need to do it in 2 steps. So that's a good thing. The shorter the method to produce that product, the better. And catalytic converters, you'll see these in cars. They're available in cars, particularly in cars with petrol or diesel generated, not electric cars, but diesel and petrol ones. So these reduce the level of pollution. They contain rhodium, platinum, and palladium alloys. So it's a mixture of metals. You would have done alloys at GCSE. And basically what a catalyst does is it converts harmful gases like carbon monoxide and nitrogen monoxide, which are these here, or nitrates, and they convert them into carbon dioxide and nitrogen. Now, carbon dioxide is not helpful because we know that it causes greenhouse gases, but if we compare it to these gases, the alternative, it's got to be better than producing carbon monoxide, which is incredibly toxic to living things. So, and nitrogen as well. So nitrogen gas, which is inert, that's naturally found in our environment anyway. So a catalytic converter sits underneath the car within the exhaust system, and that sits towards the back there. Okay, and that's it. So that's the video on equilibria and rate of reaction. So it contains everything in there. Like I say, it was designed to link GCSE and A-level. But please subscribe to my channel. There's loads of information on there for A-level chemistry. So it's called Alloy Chemistry. It's the name of the channel. So please go on there, like and subscribe. Subscribe to it to get all the updates. And like I say, there is quizzes as well. There's a quiz attached. Just click on the link in the comment box and you'll be able to get a hold of it there. Have a go at it. See what score you get and it'll mark itself. All right, that's it. Bye-bye.